Autonomous drone for power line inspections. The main issue with common power line inspection practices is that they are either limited, expensive, or both. Many power lines traverse through dense, grassy areas that have either become difficult or impossible to reach via truck since they were installed. And the sections of line that can be accessed cannot always be viewed from all sides and angles. One method of getting around this is performing inspections via helicopter. While this can get around many ground restrictions, this very expensive method is not suitable for routine inspections, and due to the limits on how close a helicopter can actually get to these lines, is still quite limited. Also, there are a lot of safety risks when flying a helicopter near energized lines, which will require the operators to have specialized training. A way of getting around all of these limitations is using a drone. The three main categories of benefits from using a drone are safety, performance, and monetary. Drones lower how susceptible these operations are to human error, can get very close, clear images of multiple angles of the equipment, and have much lower operation costs when compared to the previous method. Our design for the mechanics of the drones consists of two key pieces of hardware: the Taro X6 hexacopter frame and the Pixhawk 4 flight controller. The choice to use a hexacopter was made due to the resiliency added when using 6 propellers. If at any point during operation, if one motor fails, the remaining 5 will be able to operate enough for the drone to return to home. The flight controller was chosen to be able to use the ground station software Q Ground Control. This software allows us to plan predetermined flight paths and missions to achieve the goal of autonomy. Moving into some of the key components of hardware, each motor has 3 phases. Each motor also has its own speed controller, which has an input of a PWM motor control signal from the flight controller and has a 3-phase output. The other main peripherals connected are the GPS, landing gear, and controller receiver. In order to reduce the amount of cables needed, a junction cable is used on the frame in order to power and control each speed controller. The boxes labeled M1 through M6 are the PWM control signals. In order to achieve the goal of thermal imaging, the FLIR One Pro USB-C camera was used. While intended for smartphones, this camera is significantly cheaper than the ones made specifically for drones, and also has a thermal and visual feed, so we do not need a second camera for standard visual footage. A script was created in order to decode the footage, log frame-by-frame timestamps, capture locally, and stream footage to a remote desktop. As can be seen in the footage on the left, the thermal images captures the heat of the Raspberry Pi very clearly. And also the console on the right is displaying the center frame temperature while saving individual timestamps of it. Moving into the drone autonomy, Q Ground Control features mission planning software with 2 main categories: path missions and survey missions. On screen is an example of a path mission, where individual points are pinged on a map, and straight line paths are generated in between them. Once uploaded and executed, the drone will follow this path with an error deviation of only about 8 meters. The other type of mission used is a survey mission. In this mode, an area is drawn on the map where the user wishes to survey, and a path for the drone will be generated. After completion, it will return to home. So right here is an example of our thermal camera footage. The frame rate is 8.9 frames per second, and it streams using a local Wi-Fi network over an SSH connection. Here is a short clip to demo our flight stability. Before we go, we would like to thank Dr. Moreno, Robert Tufts, and the people at FPL. Thank you for taking the time out of your busy schedules to guide us through the design process, and we are very grateful for this opportunity.